Chapter 2.1 will be going over set concepts. So starting with the definition of a set is a collection of objects, and these objects are called elements or members of the set. So for example, the United States is a collection or a set of 50 states, and the states are the elements of the set. So for the next definition, we have the definition of a well-defined set. So we say that a set is well-defined if its contents can be clearly determined. So for an example of a well-defined set, the set of US presidents is well-defined because its contents, in this case the presidents, can be named. An example of a set that's not well-defined would be the set of the 3 best movies, because the word best is going to be interpreted differently by different people. So kind of like a hint for something that is not a well-defined set, it would be something that is similar to an opinion. So we're going to be representing a set in a couple different ways, and the 3 commonly used ways that we're going to be doing are going to be description, roster form, and set builder notation. So starting with description of sets. For a description, this method describes the elements without actually listing them out. So for an example here, let's write a description of the set containing the elements January, February, March, April, May, June, July, August, September, October, November, December. So clearly these are the months of the year. So that is exactly the description that we want. The set is the months of the year. So that's an example of a description of sets. For the next one, let's take a look at roster form. So for roster form, this method is going to list the elements of a set inside a pair of braces or these squiggly brackets. So the technical name for those are braces. So in roster form, inside of those braces, commas are going to be used to separate elements. The elements are not listed more than once, and the order does not matter. So an example of a set in roster form is going to be this set of natural numbers here. So this is a very important set that we're going to be referring to a lot. The natural numbers are going to be the set which we can denote with a capital N. It's the set of counting numbers 1, 2, 3, 4, 5, 6, 7, and so on, all the way to infinity. And this ... which I'm sure we know what it means, it is called an ellipsis, and it means it continues in this manner. Okay, so once the pattern is pretty clear what's going on with the set, you can just throw in an ellipsis to show that it just continues in that same fashion. Okay, so let's do an example here. So express the following in roster form. So let's suppose we have set A is the set of natural numbers, this should say less than 6. So the set of natural numbers less than 6, so this is going to be set A is going to equal the set, so squiggly bracket or the brace, everything less than 6, that's going to be 1, 2, 3, 4, and 5. And we don't put the ellipsis here because we just wanted everything less than 6. We knew to start at 1 because that's where the natural numbers start. Next one, we have set B is the set of natural numbers less than or equal to 45. So set B is going to be the set. Natural numbers starts at 1. So it's going to be 1, 2, 3, and that's going to keep on going all the way to 45. We obviously don't want to list out all of the elements until 45. So what we can do is put an ellipsis inside like this and say 1, 2, 3, 4, all the way up to 45. And we included 45 this time because it said less than or equal to 45. Next one for C, the set of natural numbers between 7 and 12. Okay, so this is going to be the set. So it doesn't have a set name here, so I'm just going to not name it. Between 7 and 12. So between 7 and 12 is going to be 8, 9, 10, 11. So notice we did not include 7 and 12. We just have the natural numbers between 7 and 12. That's not to get confused with the next one, which says the set of natural numbers between 7 and 12 inclusive. So inclusive is going to mean we are including the 7 and 12. So that's going to be 7, 8, 9, 10, 11, and 12. Okay, so that's the difference between not having the word inclusive there and having the word inclusive there. And then the third and last method we're going to be using is set builder notation to represent a set. And this method is used to symbolize a set. It's similar to the description of a set. And we're going to be using this symbol right here. And it's going to be read as is an element of. And similarly, we can have the symbol with it crossed out, and that would just mean is not an element of. So let's see an example of that symbol being used in this set here before we get into set builder notation. So let's say we have the set A, which contains the elements 3, 6, 8, 10, and 16. So what we could say here is we could say that 3 is an element of set A because 3 is in set A. We could similarly say that 6 is an element of set A because so is 6. We can keep on going and say 8 is an element of set A, 10 and 16 are elements of set A, and we can also say something like 5 is not an element of set A because there is no 5 in that set. Okay, so that's just a use of that notation using that symbol, representing that it is an element of the set. Okay, so let's see how set builder notation is set up here. So we're going to be using the braces again, the squiggly brackets here. So the way that we're going to read this is going to be, I'm going to read it just like we normally would from left to right. It's going to be set D. The equal sign is read as is. So set D is, the beginning of the brace is read as the set of, and the X here is read as the elements X, or all elements X. This vertical line is going to be read as such that, and then on the right hand side are going to be the conditions that X has to meet in order to be a member of the set. So as a whole, we would read this as set D is the set of all elements X, such that, and then there's going to be some conditions on the right that X has to meet in order for it to be considered a member of the set. Okay, so let's do an example. Let's write the following sets in roster form. So these are in set builder notation here. So for example A here, we would read this as set E is the set of all X's such that X is a natural number. It's in the set of natural numbers and X is greater than 10. Okay, so that is how this would be written out in words. So if X is a element of the set of natural numbers, then it's an element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. But it says X is greater than 10, so that means starting with 11, X is going to be 11, 12, 13, 14, 15, 16, and so on. So in roster form, it would look like E equals the set 11, 12, 13, 14, and so on with the ellipsis. Okay, for the next one, for B, we have A is going to be the set of all elements. X such that x is an element of the set of natural numbers, and x is between 2 and 10, including the 2 but not including the 10. So I just forgot to write the word set in the example above here. Set E is the set of all. Okay, so just forgot to write that in there. So let's go ahead and convert this into roster form. And just wrote it out in words just so we had it here. So in roster form, we're going to have to list out all of the natural numbers between 2 and 10, including 2 but not including 10. So it's going to be A starting at 2 because we're including it, 3, 4, 5, 6, 7, 8, 9. And we're going to stop there because we're not including 10 because there's no or equal to sign on the inequality by 10. Okay, so that's going from set builder notation to roster form. So now let's go the other way. Let's have some examples here. We want to write the sets from roster form to set builder notation. So the first set B, we have the set 1, 2, 3, 4, 5. So in set builder notation, they're always going to start off the same. B is the set of all elements x such that. So they're all going to start off like this. And then the right side, we have to decide what goes on the right side for the conditions. So it looks like 1, 2, 3, 4, 5. These are natural numbers. So I'm going to say x is an element of the set of natural numbers. And so usually when I write this, if you probably just realized, when I write the set, when I write symbols for the sets, I usually put like a double line on one of the lines in the letter. So x is a natural number, and x is going to be from 1 to 5. So there's actually a couple different ways we can write this. There's always going to be a couple different ways we can write these. If it's between 1 and 5, we can say that x is less than or equal to 5, because if it's less than or equal to 5, it has to start at 1 because it's a natural number and that's where the natural numbers start. If it's less than or equal to 5, that means it's equal to 5 and everything less than it going down to 1. Or what we could have wrote here is x less than 6. So it's not or equal to 6. So if it's just less than 6, then that is 1, 2, 3, 4, and 5. So either one is completely acceptable. Okay, let's do the next one. We have the set C is 8, 9, 10, 11, 12, 13. So let's start it off. C is the set of all x's such that. So starting off the same way once again. And this is going to be natural numbers once again. So x is in the set of natural numbers. And it looks like it's between 8 and 13 inclusive. So that's going to be 8 and 13. And notice that I put or equal to's on the inequalities. And what we could have done here is, once again, we could have said x is greater than 7, but less than 14. This would have meant the same exact thing because we don't have the equal sign here. So anytime we're representing the values between two numbers, we always have it set up like this with the two less than symbols, because on the left part of it, it says x is greater than or equal to 8. On the right-hand side of it, x is less than or equal to 13. Putting those together, what that means is x is between 8 and 13, including 8 and 13. Okay, and the last example for this one, we have set F, and the elements are North America, South America, Europe, Asia, Australia, Africa, and Antarctica. So in set builder notation, set F is going to be the set of all x's all elements x such that, and then we have to think, what do these elements represent? Well, these are continents, so we can say the set of all x's such that x is a continent. And that is all we would have to say for this one. Okay, so they're not always going to be numerical. They can be something like this, where in this case they represented continents. Okay, for the next thing here, we have some fundamental set concepts. So starting with terminology finite and infinite, a set is said to be finite if it contains no elements. So it's finite if it contains no elements, or the number of elements in the set is a natural number. So for example, if we have the set B right here, set B has the elements 2, 4, 6, 8, and 10. This is finite because there are 5 elements in this set. Count them: 1, 2, 3, 4, 5. And 5 is a natural number. Okay, and we say that a set that is not finite is going to be infinite. And an example of this would be something like the natural numbers. The set of natural numbers is infinite. So if we have the natural numbers, that's going to be the set 1, 2, 3, 4, 5, 6, 7, 8, and it goes all the way to infinity. So that's what these dots are saying, is that it essentially goes to infinity. It's going to keep on counting up by ones until we get to infinity. So this would be an example of an infinite set. Okay, next thing we have equal sets. So 2 sets are considered equal, which we just use the equal sign for, if and only if they contain exactly the same elements. So 2 sets are equal if they contain the same elements. So for example here, if we have the set A, which has the elements 1, 2, and 3, set B has the elements 3, 1, and 2, we want to know if these sets are equal or not. And we take a look at them. They both have the same elements, 1, 2, and 3. We have to remember that order does not matter. So since order does not matter, that means A equals B. Okay, so next is the cardinal number. So the cardinal number of a set, which we'll just use set A, the cardinal number of set A, which is symbolized with n, and the set A in parentheses is going to be the number of elements in the set. So the cardinal number represents how many elements are in the set. So for example, let's determine the cardinality, which is the same as the cardinal number, of both sets, where A is 1, 2, 3, and B is the set England, Brazil, Japan. So let's look at set A here. So we're looking for the cardinal number, the cardinality of set A, so we can write it using the symbol. It represents how many elements are in the set. There are 1, 2, 3 elements in set A, so that means the cardinality is 3. Similarly for B, the cardinal number of set B, we're looking for how many elements are in here. 1, 2, 3. There are 3 elements in set B, so that means the cardinality of both of these is 3. So what this means, and what we'll formally define it on the next page here, since the cardinalities are the same, that means that these sets are equivalent. So notice that this is not the same word as equal. So equal sets have to have the same exact elements. In turn, they will be equivalent. And equivalent sets just have to have the same number of elements. Okay, so let's formally define this here. For equivalence, set A is equivalent to set B only if the cardinality of A equals the cardinality of B. So only if they have the same number of elements. And like I just mentioned, any sets that are equal must also be equivalent, because if they're equal, then they have the same exact elements, which means they have the same number of elements. But not all sets that are equivalent are going to be equal. So in the previous example, we just saw two sets that are equivalent but not equal. Okay, so two sets that are equivalent or have the same cardinality can be placed in what we call a one-to-one correspondence of each other. And this means that every element of set A can be matched with exactly one element of set B. So let's see what this means in this example. So let's say we have the following states, which are in set S, and the following colors, which are elements in set C. So S, we have the elements North Carolina, Florida, Georgia, South Carolina. And set C, we have the colors blue, orange, red, and green. So what we can do is first recognize that the cardinalities are the same. So the cardinality of set S equals the cardinality of set C. They both are 4. In this case, they both have 1, 2, 3, 4, 1, 2, 3, 4. 4 elements, so the cardinality of both of them is 4. So what this means is that these are equivalent. And this means that there's a one-to-one correspondence. So we can correspond one element in the first set to one element in the second set. And we can do this visually here just by drawing a little arrow. We can say North Carolina to blue, Florida to orange, Georgia to red, South Carolina to green. I just completely did this just based on the fact that they were above each other and it was easy. We could have also said North Carolina to orange. We could have said North Carolina to red, North Carolina to green. It doesn't matter the arrows, I just chose them right above each other. Either way, there is a one-to-one correspondence of elements here between the sets. Okay, so a couple more things that we're going to be using going forward, but it's the last part of this section. We have the definition of an empty set. So the empty set is exactly what it sounds like. It is the set that contains nothing. It's empty, so it has no elements, and it's called the empty set. We can also call it the null set, and it's symbolized by two things. It's symbolized by a set of braces with nothing in it, or it is symbolized with that circle with the line through it. So make sure that we know both of those symbols for the empty set. And it's also important to note that this symbol right here, the braces with the empty set symbol, is not the empty set. This set contains the element. This is saying that it has the element, whatever this is, in there, which would have cardinality of 1 because it's one thing in the set. Okay, so similarly, the set 0, where we have a 0 in a set, that's not the empty set either because it contains the element 0, and that is one element, so that means cardinality of 1. So neither of these are the empty set. They look similar to what they could possibly be the empty set, but they do not represent the empty set. So let's just make sure that we have the symbols for the empty set straight. Okay, and then the last thing here is the universal set. So the universal set is going to be symbolized with a U. It's going to be a set that contains all of the elements of interest for any specific discussion. So this set will change depending on the question. So universal, we should be thinking everything. It's a set that contains everything of interest for a specific question or for a specific discussion. So when a universal set is given, only the elements in the universal set may be considered when working with the problem. Essentially, nothing else exists outside the universal set for a given problem. So, for example, if the universal set for a particular problem is going to be U, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, then only the natural numbers 1 through 10 can be used in that problem. Nothing else exists if that is our universal set. Okay, so we'll be coming back to these topics, just a little brief introduction to them. We'll be coming back to these terms and these topics in the next sections. Okay, so that is it for chapter 2.1.